Testing. Hi. Hi. Is it working? No, it's not working. Hi. Then use this one. Hi. I guess I'll start. Can Zoom people hear me? Okay. Let's get started. So I just briefly review what we have done in Tuesday, and quickly what we aim to try to do is hopefully we can finish the dispersion. We'll finish central tendency easily, and dispersion, and let's see we can finish the shape. And then once we're done, then we'll talk about relation, correlation, and hopefully we finish the theory part today. If not, then will be next week. Just a brief reminder, what we're doing here is we are talking about the topic 1 in descriptive statistics, which is saying that try to use the data and try to see if we can look at some characteristic or property of the data, and that would be useful for our later analysis. Okay, and we learned that in particular we learn 3 different ways to do it. There will be central tendency, another will be dispersion, and the shape. And in the last class, we go in detail about the mean and talk about the definition of median. And then today we will cover the median mode, and then we will talk about dispersion. Okay. So just a gentle reminder of the mean. Mean is exactly just very simple, just adding up the observation over total number of them. And we actually learned that what is the let me try to do the full screen. Do full screen mode again. And it exactly is in the center of the data in the sense of distance, which means that the location of the mean, you calculate the distance from all the observation to the left will be same as the one to the right. Okay, so and this require you to say the distance between observation would make sense. Okay, just to remind you that the mean would be most meaningful when we talk about numerical data. Okay, when we talk about ordinal data or nominal data, mean lose its attraction because of the idea that is in terms of distance. And second, because of the equidistance is subject to problem outlier. And of course, as this example show, when we have a outlier there, there's a problem. And we learn how to solve it is by trimming data or renderizing the data. Okay, there are the 2 ways to solve this problem. And there are several ways to generalize it is look at the, say, weighted averages, weighted mean, and also there are certain other mean that will be useful for other purpose. It's like geometric mean. There's some reason why you want to use it. And last time we stopped at this particular slide is because of the mean is calculating distance. And probably everybody knows how to calculate median is exactly middle guy, right? If we have odd number observations, say 3 observations, right? The second one is exactly the middle. That's no problem. Just n plus 1 over 2, which is a integer, n plus 1, right? Odd plus 1 is even over 2 is also a number. Okay, that's no problem. But the problem is when you have even number observations, say you have 4 observations, right? Where's the middle, right? Suppose it's 2.5 something, right? And 2.5 will be the average of 2 and 3, right? So that is the reason why you have n over 2 plus n over 2 plus 1, right? And we learned last time, this is rather a complicated formula, right? Because odd, you have the one guy, even the 2 guys middle. So there's a good way to summarize it is half of this function, right? The floor and the ceiling, right? And that will be the idea, right? Because just to remind you that if n plus 1 over 2 is an odd number, right? In that case, right? This is a integer, right? So it's integer when you apply floor or ceiling has no impact. They're the same. So half of the same thing plus half the same thing is what is supposed to be, right? But when it's not an integer, right? So this take the integer part, so that's why you have this, and you take the integer part plus 1, you get this guy. Okay, so that is exactly what it means. Okay, and I just remind you that why we want to write in this rather complicated way is because when you learn programming, or possibly when you go to the Python optional tutorial or our tutorial, if you have to write the median function by yourself, then you have to use this formula, right? The thing you do in Python, or you can do in Excel, B.B.A as well, or R, is to sort the data, right? You calculate the n by itself, and then use the run function, run up function to get this 2 number average. Okay, if you know programming, then easily you can envision yourself doing this quickly. Okay, I will leave you in the tutorial to ask, or you can try it out yourself. Okay, so that is the reason why we talk about this. Of course, if you don't like this formula, you can just do whatever you have here, right? If odd, just take the middle guy. If even, you just take the average of the middle 2 guy. Okay, so obviously by definition is the middle guy regardless of the distance. Okay, so the good thing is you just look at exactly the middle, right? So it doesn't matter what the number before the middle or the middle, right? It doesn't really matter. So this is good, right? Because it doesn't affected by outlier. But in some sense also bad, because the data share the same median, you can't tell much, right? Let me say, suppose I have data, we have odd number of data, right? Suppose we have one guy here, one guy here, one guy here, right? 3 observation, right? We know the median is what, right? The median is middle guy, right? What I mean is this is a number line, right? The more to your right hand side, the larger, right? And look at the other cases. You have another data is also here, here, and here, right? The median is still the middle guy, right? Only 3 observations, the red data set, right? And the median same. Okay. You may say, okay, the same median, but you would not think, you would think, say, the median for the first data set is better than the second one, right? Because in the first data set, the data are closer to the median than the second one, right? The median doesn't tell you anything, right? If you look at the other data set, also the same. If you have something like this, and this, the green one, okay? Still the median is the middle guy, okay? So that is a slight problem median is it doesn't really care about how it looks like, okay? So that's why later we talk about dispersion. That would be an important thing to take into account, okay? But in the meantime, you can see the median is independent of how the outlier looks like. It's a good, but in some sense, it's an issue. Okay. And especially when your data is good for ordinal data, right? Because remember the thing of the ordinal data is Likert scale, right? Whether you disagree, strongly disagree, those kind of still 1, 2, 3, 4, 5, right? When there's median, usually at the end you only have say 3 or 4 or 5, just several value, right? Because the middle guy, right? Most likely is either 3 or 4 or 5, just like the one you take. You don't get 3 from 5 or something, right? So median in that sense may not be that useful. So that's why in practice, although mean is not good for nominal data, right? Not for the ordinal data, right? The Likert scale, but you still see the online website, the Amazon, or all the things they still use the average. It's because using the median actually don't tell you much, because either it's 3 or 4 or 5 or 1, 2, 3, 4, 5, right? Usually you don't have 3.5. It's rarely the middle guy is between 3 and 4, right? Most likely you just had the same thing as the original data. Okay, so that's why median in some sense is good, but not that good, right? In some sense. But just to remind you that when the data is skewed, right, median is good, right? You look at the green one, it's very likely to be like income data, right? And median will be good, right? Because like the income data you observe in the real world look like this usually, right? You have a bunch of people here, okay? And maybe some millionaire here, but most of people are here, okay? So median would not be affected by a bunch of rich guys, not going to move it. Okay, of course, you may say, okay, let's truncate or linearize it. Okay, also fine. But median will be a more useful way. The reason why you cannot really do the truncating or linearizing is not that good is because it's hard to tell what is top 5%, top 1% is not really entirely clear. But median, you don't have to choose what is the percentage you try to linearize or trim, because median is just median, right? You don't have to think about what to cut. So I hope this is clear to you why we use median. And quickly, you just go to example. I think you know very well. I just very brief. So 1, 2, 3, exactly middle guy with 2, and 1, 2, 3, 4 will be, because it's even number, just take the middle 2 guys, 2 and 3 the average. Okay, and it's so if you change last guy to 40, it doesn't change the number, so it's still 2.5. Okay, so I hope that is clear what's going on. I'll just be quick here in case a question asks me during the break. So I hope you know how to calculate mean and median. That's not an issue. Now the next thing is mode. Okay, mode is it's not talking about center of the data or middle of data. Okay, instead it's asking the most frequent value. Okay, it appears the most. Basically, what you learn is from the frequency table. Okay, counting how many of them, the one appear most will be the mode. Okay, here, although mode is easy to calculate, okay, and it appear most, there's several technical complications here. Okay, first is what happens if you have multiple observation has the maximum frequency, right? In that case, usually people would use the multi-mode, right? The multi more than one. Okay, so then it is not very useful, because compared to mean and median, we only have one number here. If mode is say multiple number, what does that mean? Okay, suppose you're asking income data, you're telling me, okay, the mode of the income is say 20,000 Hong Kong dollar per month, and also $100,000 per month. What does that mean? You give you two numbers very extreme. It's not clear what does that mean for the mode, right? It's not unnatural to see this because sometimes the data is like bimodal. If I draw a frequency polygon, something happen like this, it's not unusual. Okay, our data is this one. The horizontal is the frequency. This is the frequency polygon, right? Or you can think about a histogram, right? Then you can see this number and this number are the maximum frequency, right? And then telling me the mode is all these two number, or even you can have a complicated thing. It's like this light wave, maybe the three mode here. What do we learn from that? Okay, it's easy to calculate, and it also even apply to categorical data, right? Not even ordinal, even categorical you can apply, right? So that is an issue. Another issue is here is in most of textbook, people, if every data only have frequency of 1, okay, many textbook would say there's no mode. Okay, and for our purpose, we make our life easier. We just, even if only appear once, we say everything is mode. The reason is this is sometimes how you write your software package, right? Because you can easily find the most frequent thing. So that's how we define it this way. Okay, just to make sure that this will be a well-defined concept. Rather than a mode don't exist, we allow that if everything appear once, everything will be mode. Of course, in that case, if everything appear once, then it's not very useful. Okay, that means what? If your data is a continuous measurement, mode will be useless, more or less, right? Look at the Hansen index, right? Every day can be a number that can be a lot of different number, right? Can be allowed. Looking at the mode will be useless, right? But if you look at, you simplify the data, look at whether the stock market has gone up or gone down, right? Then it can be used, right? You can look at the mode, right? So that is how people actually use it, right? A lot of some of the data that have been used is like technical indicator. Look at past months or past 2 weeks, whether the stock market go up or go down, right? As a technical indicator, the strength, right? So if you simplify in some way the data, mode will be still useful. Okay, so that is how you use mode, right? When it's continuous variable, you have to simplify in certain way such that make sure that data appear more than once, or otherwise it's not very useful. Okay, so that is how we use mode, and I think everybody knows it. And just to remind you that when you use mode, it's most generous way to do it because it also applies to categorical data. Okay, also apply to the nominal data as well, right? So this a little bit somewhat useful thing to know. And just quickly go to here, as I want to remind you that in general, you look at some textbook, when you have 1, 2, 3, 4, everyone appear twice, appear once, they will say there's no mode exists. Okay, and for our purpose, we just do it 1, 2, 3, 4, just to make sure that it consists. I think it's consistent Excel or R the way I do it. The reason I do it because I try to consistent with some software package, but otherwise it doesn't really matter anyway. And you have say 1, 2, 2, 3, 3, 4, then will be, because 2 and 3 appear twice, then 2 and 3. If you have 1, 2, 2, 3, 4, then it's 2. Okay, so in some sense you can see here is mode is rather sensitive as well, right? In the case where you have one, there's an observation here comes in, and that's 3 gone, right? So in some sense it's okay, but it's not very good, right? But sometimes we do use it, right? Some people, sometimes we say, okay, what is the most used transport to come to the campus, right? Then people might care, right? And people care that. So it's not something is not useful, but it's still rather useful to look at the mode. But in the case look at the mode, you would probably not only look at the most frequent one, right? Also, maybe you also care the second most frequent one, right? The mode after the first mode, sometimes you want to care as well. But anyway, I hope it's clear. The three things, you know, the mean, median, mode, how to use it, and what the caveat of using it. Okay, and I would expect you know how to calculate without difficulties because they have been included in your high school syllabus. So what I want to look at it before the break is try to cover some of it. Range, interquartile range, variance, SD, and CV. Okay, and all these things will be super useful, I would say. Okay, the first one is immediate trivial, right? Because this person is asking, look at how data are spread out. Okay, that is what the measure is. And one immediate, the most easiest thing to do is look at how spread out, look at the maximum minus the minimum, right? So look at the difference between larger and smallest. So is the range is divided the max minus the mean, right? Or if your data is sort from ascending order, right? It's xn minus x1, okay? So obviously this is simple to calculate, right? And obviously you can see same as the caveat we said about the mean. If the outlier are there, there's a problem, right? Suppose the data with the Bill Gates and Elon Musk income data, they are making huge amount of money, right? With then the range will be large, right? So that is a problem. Okay, just to see the example here quickly. When you have range, we just 1, 2, 3, 4, 5, 5 minus 1 is 4, and 1, 2, 3, 4, 50, 50 minus 1 is 49, right? And again, the same residual would work here. Suppose if you trim the data, or send the data, or windsorize the data, right? You count the range, will be more reasonable, right? Suppose you are going to windsorize the data, right? 50 become 4, right? And in that case, the range will be reasonable, right? So that means that range is not that bad, right? Once you allow yourself to trim the data or windsorize the data, okay? But I'm not going to talk about this here, but you know, when you have a outlier, then you can do some winsorizing or trimming can help you to solve this problem, okay? So this range is easy. I don't think I need to go more on that, okay? Should not be an issue, right? But you can see this range when you apply to ordinal data, right? Such a likelihood scale will be almost useless, right? Suppose you have every single element, single every option has been chosen, right? Some people very strongly agree and some people strongly disagree. Then the range is always 4, 5 minus 1, okay? So the range in that case will be useless, all right? So the next thing is, when I talk about range, is to improve it instead of looking at the outlier, looking at the biggest minus the smallest. We look at something a little bit more simpler, okay? So let's see what we're going to do, okay? So what we're going to do is instead of looking at the distance between the biggest and smallest, look at something distant between some middle part, okay? By middle part here, we have to introduce a concept called quartiles, okay? By English, probably you know, quart means divided into 4, quarter, okay? Quadrants, okay? Quart means 4. Tiles, okay? By English means squares, okay? Quartile means divided into 4 squares, okay? So if you divide the data into 2 squares, okay, then you are cutting at the median, right? And if you cut the data in the median first and median twice again, then you get 4 parts, okay? So what I mean is, here, suppose I have the data like this. I consider this data. right? And if this is smallest and this is the biggest, right? And I cut at the center, somewhere here, then the median, right? And if I look at the first part and consider median again, right? And I do the same for the other part, then another median again, right? So we will call, because it's 4 part, right? And this guy we will call Q1, this is Q2, this is Q3, okay? Q2 is median, right? And sometimes look at software, sometimes they call this Q0, and sometimes they call this is Q4, but later we'll talk about Excel, then we see what they are, but we focus on Q1, Q2, and Q3, okay? So let me remind you what's Q2. Q2 is the median, okay? And once you do the median, you do the median again for the first part. That gives you Q1. And median of the later part is Q3, okay? And remember what's the range here? The range is the largest and the smallest, right? Is the range, okay? And the range, maybe I use the other color, it's not very clear here. Range will be just like the orange one, right? It's the smallest and the biggest difference. Orange, right? Basically Q4 minus Q0, right? And as we can see in this diagram, if Q4 and Q0 move around, then the range change, okay? So one way that you want to avoid the problem of extreme value is looking at this Q3 minus Q1, which we define as IQR, interquartile range in the next slide. But there is the idea, okay? Instead look at the middle, which is 50% of data, look at the 75% and 25%. Okay? Is that clear what we are going to do? Okay, just let me repeat once more last time. Median is the Q2, okay? Look at the median of first half is Q1. Median of second half is Q3. I want to look at, instead of the biggest minus smallest, looking at the difference between Q1 and Q3, okay? 75% to the 25%, okay? And to define this properly, right? We know that the median is n plus, is this guy, right? The median is this guy, right? 1/2 of n plus 1 over 2, right? Because n plus 1 over 2, right? Of course, if it's a odd number, this is well defined. If even, we just halfway of the 2, right? So you can easily see we can extend this idea, right? So be 1/4 of n plus 1 and 3/4 of n plus 1, right? Right, so that is the definition. Okay. So intuitively, it's simple. If n plus 1 is a multiple of 4, right? It's divisible by 4, then this definition is simple, right? Because they're integer. There's no issue there. But if n plus 1 is not divisible by 4, there's a lot of issue there. Okay. And how to define Q1 and Q3? There are no universal rule, I would say. And if you look at, say, software package R, at least there are 9 different ways to define quantiles. And even look at the Excel spreadsheet, at least there are 2 ways to define quantiles. Okay, so I think we focus on the way that is easier to calculate and make more sense. Okay, of course there are other ways to make sense, but we focus on one way to do it. And you notice that some of you learn the quantile in the high school, they will look at different things. Okay, so the IQR, as I said, is Q3 minus Q1, and is affected by outlier, less affected by outlier. Okay, and here a technical thing is how to define Q1 and Q3 is an issue, okay? And of course, all this method would make little difference when your data has a lot of observation, okay? When the sample size is huge, say suppose look at applied to data more than say 10,000 data or more, even if data more than 1,000, you don't observe any big difference of this calculation. It's not being issue. But when the data set you have is like several hundred or even less than 100, okay, then the method here is some issue, okay? And I put method 1 and 2 here is some of you learned it in high school, and different textbook may use 1 or 2, depends on which textbook you're using, okay? And we'll talk about method 3, which I think is little better. And you look at Wikipedia or other website, or it will be using this one. And I talk about method 3 because this is used in Excel spreadsheet. Okay, so you will see this the one. That's why I talk about method 3, because this is the one you can reconcile with Excel spreadsheet. Okay, and method 1 and 2 is very simple. Basically, what they're doing is look at the median. Okay, median and median again. The difference is, remember the idea. What we do here is the data set. Look at the median. Right, the median is a date. If the median is exactly, if the n is odd, okay, if n is odd, then n plus 1 over 2, okay, is an integer, right? Say maybe I put in this integer. In this way, whether you keep this data into the first half or second half will be an issue. Okay, let me talk about this here. So I hope people can still see here. The idea is this, right? Suppose a data set here, okay, and we calculate the method 1, method 2 is like this. I take the median of data, right, and then this is called Q2 here. I hope you can see the back. And what we're going to do is cut this again with Q1 and cut this again with Q3. Okay. So the method 1 and method 2 here is do median again, median first, and median again, median again. Okay. If this Q2, the problem is, if this Q2 is coming from the data itself, okay. Suppose you have odd number of data, okay. There is exactly the guy in the middle, exactly median. The problem is, would you include the median into the first data set or not? Okay. If you include it, okay, then method 1. If don't include it, then method 2. Okay. Let me show you the example in the next slide, and you will see what is method 2 before we go to more elaborated method 3. Okay. Look at this 1, 2, 3, 4, 5, and later we contrast it with example 2, 1, 2, 3, 4, 5, 6. Okay, one is even with odd. Okay, 1, 2, 3, 4, 5. Obviously, the middle guy is median is 3, right? And method 1 would say we include the median into our calculation. Okay, the first half of data is 1, 2, 3. Okay, 3 numbers. Median is the middle guy. 2, so Q1 is 2. Okay, and second half is you include median as well. 3, 4, 5. Okay, the median is 4. Okay, Q3 is 4. Then the interquartile range is 4 minus 2, which is 2. Okay, look at method 2. Method 2 will be you are not including the median itself when you calculate the first or second half. Okay, the median is 3. Okay, but you don't think about the median. Okay, everything before 3 is 1 and 2. Okay, and 1 and 2 guy, the median will be the middle, right? 1.5 is or half of way. That is why 1.5. Okay, and The second half will be 3, 4, 5, but you don't care about the 3, right? So it's 4, 5. 4, 5, the middle guy is 4.5. So it's 4.5 minus 1.5, that's 3. Is that clear what's going on here? Is that okay? Any question if I need me to repeat? Is that okay? Okay. So look at the other example. Okay. In that case, we have even number observation. Okay. And then we have 6, right? 6 plus 1 is 7. 7 minus 2 is 3.5. So actually the median will be between 3 and 4, right? Average of 3 and 4, actually 3.5. And in that case, the median 3.5 is not included in the data. So that's why you just look at the median is the 1, 2, 3, right? Give you 2, and 4, 5, 6 give you 5. The IQR is the difference is 3. But in that case, the method 2 will be same as method 1, right? Because whether you include that is not an issue. So that means that when you have even number observation, method 1 and method 2 give the same thing, right? But if odd number, they're different. Okay. So some of you I think in the US, they use the method 2, and in Asia, they use method 1. Of course, some area, maybe Malaysia, Indonesia, or Korea, they use different things, but more or less along this line when you're in high school, learn this. Okay. And that is not that convenient, as you can see, because it depends how you calculate, depends on whether odd or even, right? Writing a formula will be complicated. You can see the median is already complicated. With this, it's a little bit complicated. The question is, can we have a systematic way to calculate it? Okay. The answer is yes. Okay. And this is a systematic way to do it. And what we're doing is we'll use what we call a quantile function. Okay. Quantile function. Okay. And what we do is the following. Actually, it's a rather simple idea. Okay. Although the formula looks complicated, let me write it here and you will see what it means, right? And remember our Q1 or Q3, right? The formula, I just write the formula here, is n plus 1 over 4, right? 3n plus 1 over 4, right? These are the formula here, okay? And the question here is, if this is integer, it's not a problem, right? What happened if this that common places, right? And what are we going to do? Okay. Suppose the number, right, is in this example. Okay, look at the example. Forget about this formula first, and we'll justify this later. Okay. Look at this data set. We have 5 observations, right? So according to this formula, n plus 1 over 4 is 5 plus 1 over 4, which is 6 over 4, right? 6 over 4 will be what? No, let's do this. Okay, so 1.5 means what? Very simple, right? If you know the median idea, 5 will be 1.5 will just, I take the average of the first guy and the second guy divided by 2. Right? So halfway of 1 and 2. Okay? And that's not easy. Okay? And this is, you can write other way around, is you can write this. you can write x1 plus halfway x2 minus x1. Okay, or 0.5. Okay. So 1.5, half of this is equal to x1 plus halfway of distance. This is the same as this guy. Okay. And you will see from this formula, again the same, 3 times 6 over 4, right, is 18 over 4, which is 4.5. Okay. Okay. So will be 4.5. You can say 4 plus halfway of 5 minus 4. Okay. So that explains the formula we have here. Okay. For this example, we have 5 data points. Okay. Q1 is the number 1.5 data, which is 1 plus halfway of difference between 1 and 2. Okay. So that's why we have this formula here. 1.5 is 1 plus halfway of 1 and 2. It gives you 1.5. Okay. And same here, because this 4.5 will be number 4 here plus halfway of 4 and 5. Okay. That gives you 4, and halfway of 4 and 5 give you 4.5. Okay. The difference is 3. Okay. And in this case, it coincides the method 2. Okay. And again, I repeat why I want to do this is because this is what Excel gives you. Okay. So you need to understand why the Excel gives you this formula. Right. This is the reason it gives you. Okay. And is that okay? If okay, let's go to the next one. Okay. This one is a little bit trickier, but you can see the same trick goes on. Okay. Now, n here, if we have 3, so you have 6, n is 6, right? So this formula tells you 6 plus 1 over 4, which is 7 over 4, right? What is 7 over 4? 7 over 4. Sorry. 1.75. Right? So what you should get for this guy Q1 will be very simple. Just get the first guy, x1 plus 0.75 of x2 minus x1. Okay. And you may ask why this formula 0.75 times distance. Okay. The idea is what we call linear interpolation. Okay. Actually, look at this graph here. Maybe a little bit difficult to see from this one. Let me draw another one that is less intimidating. Okay. Now, what we want to do is look at this. We have x1, x2 here. Okay. The question what we want is x 1.75. Right? Because x1, we know in this case is some number. Just 75 ID. 1 and 2, 1.75 here. Okay. And this value is x1, right? And this value is x2, right? And the question is, what is 1.75? You draw a line here, okay? Linear population. You want to go from here, 1.75, to here, this is x1. Okay? And how you get this number, right? Is by similar triangle idea. Right? Similar triangle idea. Okay. How to do similar triangle here? Let's look at the blue and the red in this diagram. Okay. The blue and the red are the similar triangle. Okay. And you learn from math, right? Or the tangents problem is this, the same side, the ratio, the same side to the other side, right? So alpha over 1 is same as this. This case is, look at this, right? Alpha is 0.75 over this distance is 1. This is 0.75 here, and this is 1. Okay, this over this, okay, would be same as this is x 1.75 minus x1 for this height, and this height will be x2 minus x1, right? X1. So they are the same. So this over this should be same as x1.75 minus x1 over x2 minus x1. That formula over there. Okay. And you can see by cross multiplication, you get this formula. You multiply this to here, move to the other side, right? Oh, or you multiply this and move here. Okay. Cross multiplication, move to the other side. This is the formula. Right? So of course, you don't need to remember this thing, but it's very natural. This is what this quantile function is. It's linear interpolation, right? So basically what we get here is we have a number 1.75. What we're going to do is look at the integer part, is the one you get, the number here, and look at the decimal part, round up here, round down there. That's the formula there. Okay. The k is the integer part of this is round down part, right? And alpha is the decimum places, right? And then 1. Okay, so that is how you get this. That's how you would get this formula. Okay. And oh, sorry, I should have a break. But let me finish this quickly. I didn't know because there's no clock in this room. Sorry. So quickly, I finished this method 3 for the interquartile range. Okay. Now in this question is rather simple. We have n is equal to 6, right? N equal to 6. Okay. 6 plus 1 is 7. 7 over 4, I think it's 1.75. Okay. And you get the integer is 1. The decimal places is 0.75. So you get the first item plus 475, right? And the difference give you 1.75, right? And same, instead of 0.25, you get 3 over 4, which is this guy, right? Okay. And it's 5.25. Get the integer, get the decimal places, get the integer 1, right? X5, and 0.75 of the next guy minus itself, okay, give you 5.75. Okay. And in that case, the IQR is 3.5. Okay. So this explains why we need to talk about method 3, because method 3 can be different from 1 and 2. Okay. So that's why when you look at when you try to use the Excel spreadsheet to calculate quantile or IQR, it will be different from what you learned from the high school, right? So for our purpose, we will always use method 3. Okay. So if you ask me what to do in exam or you do test or assignment, use method 3. I talk about 1 and 2 because some of you learned it in your high school. And method 3 is a consistent way to do it, and Excel to do it as well. And R you can do it as well. So the reason why, that's why we want to focus this. Okay. So sorry, I overrun a little bit, but let me stop here. And after the break, we will continue with the variance and all those kind of exercise. Okay, let's have a break. I walk around to see if you have any question. Let's resume at 4:30 as usual, 5:30 as usual. And you in what is your I need your yes. 1155 Let me see how can I add. Wait a second. I have to think about how to add. Pause 2. Wait a second. 1155 Use it. Yes. Maybe you can do it. Yeah, should be here. It's there. Done. Let's go. Yeah.
So I have still a question about it. So this question is depending from the method 2.
No, method 3.
But it originates from
Method, okay. Method 1 and method 2, we just look at the median. So look at the median, look at the second Q2, and then look at the first half of the median and the median again. So that will be different from what we learn is we don't look at the median. We don't rely on the median itself. We just calculate this M plus 1 over 4, where it's located, and you take the interpolation.
So just use the
Yeah, just the quantile and just the quantile answer. So it's 1.7, say suppose the limits. Say 6.75, the over is x6 plus 0.75 x7 minus x.
So why do I need to add 5?
Oh, that's how to get the middle. When you have 3 data sets, where's the middle guy? 2 plus 1 over 2.
Oh, okay.
Same. When you say suppose you're 100, okay. Suppose it's 99 or 100, right? 100, okay. And plus 1 over 4. Then you calculate. I don't want to calculate. 1 over 1 over 4, 2525. Okay. Okay. What we're going to do is x25 plus 125 x26 Q42. You mean Q3? Yeah, Q3 over 7. When you times 3, this line is 3 times this line. 4, that is 75, 75. X75 plus 0.75. Yeah.
It depends on
Yeah.
Oh.
It depends on the rank. The rank is not 1 to 5. It can be 1, 20. It can be any number.
Oh,
I don't know whether I answered the question.
For example, the division results like 76.8. So this one is x77 minus x76.
Yeah, but then there cannot be point. It can only be 0.25, 0.75, 0.5.
Oh,
Because divided by 4.
Oh, yeah.
But I mean, if that is the
For
case,
example,
yeah. I mean, because the quantile function defined for anything. So if any integer, if any one would work, but for quantile, it's always.
It's basically the integer like after that one.
Yeah.
Okay.
That is defined, right? This is the definition is alpha. Alpha is this minus the. This is the decimal part. Because this is the original one minus, right? Because this is 75. This minus this is 75.
The alpha is the decimal is given.
Yeah, that's decimal base. This is the integer part.
From the
Yeah, for the calculation. This 2 powers here. Happen 100, but anyway. Happen to be lucky. I shouldn't use this one. I should use another one. Oh, because median is calculated this. So median is actually is one. It's divided by that is 4/2. So that's why that is how we define it. How we define it. We just define the same thing. The formula applies always. The same formula. Is that okay? Okay. Yes. If there's one, as I mentioned, there usually is no. If we have time, we may give some quiz, but usually no. No quiz. We just some multiple choice question. Yeah, like I can.
Just in class.
Yeah.
Some random.
Yeah. If I give, I mean, of course.
Okay.
But no, I would say we don't have time. But I just put it there because we have one.
Yeah. And there is an interval estimate. Yes, there is.
No. That's not the same. We'll probably have.
Oh.
It's in the estimation.
Okay, so we don't have anything.
No. Yeah. The Q is always the same as why by this place it could be only by mathematics. What would you mean by Q is okay? This is the meaning of this one. Oh, you're asking me why this formula same as the one?
Yes, why they have the same results.
Oh, you're asking me why n was 1/2 plus. Why this exactly seems to be not? Oh, this guy is about half. Yes, he must be or nothing. Or if nothing, then same as this guy. If they're half, then we can prove it. But very good question. Thank you. Any question from the Zoom? So let's resume. So quickly, where is it? Oh, wheel. Okay. So before we continue, just to remind you again why we do this a complicated thing is method 1 and 2 is something you might have learned in the high school. And method 3 is the thing that is used in software package, so that's why we learned that one. And the calculation is not very difficult. Is look at this formula again, n over n plus 1 over 4, or 3 times n plus 1 over 4. And some of you ask me why n plus 1, right? Because that's how you calculate the median, right? You're going to complain n plus 1 over 2, right? So the same idea here, okay? It's again median and median again, okay? The idea is very similar. But when n is a small number, that makes a difference. When n is a big number, n plus 1 over 2 or m over 2, the same thing, almost the same thing, right? So I hope that's clear. And if you're confused, you can do some example. Should not be a difficult part, okay? So before we proceed, I want to mention one chart that is called box plot, okay? This box plot is something probably you may not have learned before, but it's useful to look at the range and interquartile range and median, okay, and quantiles. So look at this example here. Example 1 is the 1, 2, 3, 4, 5, okay, and 1 is the minimum, 5 is the maximum, right? And 1.75 and 4. I think the 4.5 are the Q1 and Q2, and this is Q2, this Q1 and Q3, right? So this is box plot, okay? And you can see from this diagram very easily, right? This guy is the range, right? And this guy is the interquartile range, right? Same, you can draw it for the example 2, okay? And this box plot is very useful when you try to visualize the range, interquartile range, the median to any audience, okay? Because look at easily, usually you compare 2 different observations, right? You can see, you can argue the range and interquartile range is much larger in example 2 and example 1, right? So that is how usually you use it. You try to look at different groups and the interquartile range can tell you things, right? And this is very useful tools, okay? The next 3 we will have what we call variance, standard deviation, and coefficient variation are the most popular thing you will see in the real world, okay? And here is variance is we will be using all information available in the data, because the problem of interquartile range is not every single data is used, right? Still look at the 25% and 75% of data, right? If there's something move but doesn't change the ranking, right? Still have no impact. What I mean is, suppose the data is 1, 2, 3, 4, 5, 6, right? If 6 goes up by 1, IQ are the same, right? Or if there's some change in number 3, maybe 3.5 or 2.1, right? Because number 3 is not used in the data set, right? Calculation. So if you change 3 to 3.1, 3.2, the same thing happened. There's nothing changed in data, right? So that's the reason why we want to. Oh, what happened? Okay, that's why we want to look at something using whole data set we call variance. Okay, so how to define variance is the average square distance from mean. Okay, how we define is look at each data point, x1 up to xn, you minus the mean and take squared, add them all up over n. Okay. Okay. And the first question comes to your mind is why we have to use square. Okay. Why we just don't use absolute value. Right. The answer is Yes, there is a measurement using absolute value. Okay, and that the reason why we use square instead of absolute value is if you learn calculus, you learn when you have square, it is differentiable. If absolute value is not differentiable. So in short, it means that the mathematical property of variance is nicer than taking absolute value. But that being said, in recent computational development, absolute value do have merit. Okay, and there's some time we look at the absolute difference. But for our purpose, for our class, we use the square. Okay. So in here, what technical it means is how each data different from the mean is average distance. Okay. If you take the absolute value, it's average distance. But now we have a square difference. Okay. So what of course having a squared distance has a benefit of calculation easier, right? But the problem is it will be saying that the data further away from mean will get exaggerated, right? Because if you're far away from the mean, then you get square, then the measurement will be much larger, right? Of course, some will say this is a good thing because you really want to double count those, okay? But that's another issue. There's a feature of the something, but sometimes it's not that good, okay? But anyway, this is the measurement we want to calculate, okay? The measurement is the square distance from the mean, it's average, okay? Okay, and then the next part is you can see the other one here. Below we have adjustment factor n over n minus 1. Okay, you may ask what it is, and later you will see why we want to divide by n minus 1. Okay, and if you look at Excel later, we will look at it. This one is called population variance. This is called sample variance. Okay, and when we will answer you why the second one is better, is when we talk about estimation in our topic 5. Okay, yeah, topic 5. We talk about why we look at n minus 1 instead of n. Okay, and the idea is, in short, is using the sample one will be more accurate than the original one. Okay, so to put into perspective is this is the one we're interested in. Okay, we want to know the average one. Okay, but when we collect sample, the one we calculate, if you calculate the same formula, it's not so good. So what happened? What we want is when we calculate, we want to calculate this to estimate what's going on. Here is better. Okay, so it's a little bit convoluted. Let me repeat the statement again. Okay, regardless of what we want, the orange one is our goal. This is something we want to know the data. Okay, but in practice, when we collect sample, when we do calculation, if you do the same formula to do the calculation, there's a problem. Okay, you usually tend to underestimate the variance. Okay, so we have to multiply this. Okay, or instead of divided by n, you divide n minus 1. That will give us a better result. Okay, and the reason why this is better, we try to justify this when we go to topic 5. Okay, we'll talk about estimation. That will explain why we have this formula. Okay, but this formula in your mind is we want to calculate this guy. Okay, is that clear what we're doing? Okay, the orange one is always we want to do. Okay, but when you actually do the data, you would do the below one to estimate what's going on there. Okay, we're always interested in the average deviation. Okay, square deviation from the mean, right? But to calculate, we use the one below. Is that clear? Is that clear what we are doing? Okay, so in Excel, this is called population. This is called the sample one. Okay, And I think everyone learned it in high school, so I just rather quick here. Okay, so this is the, oh, sorry, I think there's a typo here. Population, okay, the population sample variance for data 1 to 5, okay, and very quickly, you will see I have this table here. The reason why I have this table here is to facilitate you when you do Excel. Later, when we do Excel, we'll see this is the very convenient way to do it, okay? And you list the data in the column form, okay? And you calculate the mean in the other column, okay? And you do operation one by one. First, calculate each observation minus mean, okay? And do it for every single observation, okay? And then you square each observation, okay? From the last column, and then add them all up, okay? And you divide it by n, which is 5, you get 2. You divide this by n-1 is 2.5, okay? And as I said, because you always, almost all the time, you do the sample, okay? So always you use this formula here, okay? But when you happily, you have the data of everything you want, okay? Maybe you have census data, you're lucky, then you can use this one. But of course, as you can see, n and n, the denominator is only different if one is n with n-1. When n is super big, there's no difference, right? So that means that when you're doing census, you have a 1 million data point or several million data point. Actually, it doesn't really matter which one you're using, okay? But still, I mean, you use n-1 because you have better property, okay? Now I'm not going to go to detail. I think this is something you should have learned in high school, so I just rather quick here. And the second one is what we call SD, or standard deviation, right? And this one is very simple, okay? And just to take the square root of the variance, that will give us the formula. And again, as I told you, for our purpose, for most purpose, this is the thing we want to calculate, right? It's not divided by n, but n-1. And the idea is similar, okay? This is how you do the estimation. And the reason why we talk about SD instead of the variance is because of when you square, the measurement unit is a pretty unnatural, right? Suppose you're looking at the height, right? It is say in centimeter or millimeter or meter, right? But when you have variance, it will be meter square, right? So that's why it's not very natural. So we will take standard deviation. Okay. And also turn out to be standard deviation has an important nice property, though. That's why almost everything we focus on SD. Okay, because you know the bell-shaped curve you learn right later, or you learn in high school, you know the 3SD rule or 2SD rule, those kind of things based on SD, not the variance. Okay, and there's a reason why you want to focus on SD rather than variant, but this is the thing we do. Okay, and the last one is just a very simple thing, is to what we call the rescaling the data, right? This one is to get back to the original unit, right? CM is still CM, right? Not CM square. And here is we go one more step, is get away the CM as well. Okay, so what you're going to do is you divide by the sample mean. Okay, and usually you multiply by 100. Okay, and you want to be a percentage. Okay, and why you would want to care about this CV, why you want to divide it by mean, okay, is for comparison purpose, right? Say, for example, I want to look at the dispersion of, say, midterm exam and the final. I mean, we don't have midterm, okay, just to make sure that we don't have midterm in our class. But anyway, suppose a midterm, we take a midterm exam and we have a final exam, right? And very often the final is more difficult than the midterm. Or right? And the final will be usually have lower mean, right? And saying that the final has lower variance, usually, right? It's not very meaningful, right? Because you should have divided by his mean to make sure that it's not truncated by that, right? To put in perspective, put it this way. Midterm maybe have maximum of 50, okay? Because you have less question to make, okay? And the final may have 100 marks, say, okay? And it's easily you can see with even things are same dispersed, when you have calculated variance of SD, the final will have a much bigger number because fluctuation between 100 and 0, right? The midterm is 150, right? So in order to make sure that you have fair comparison, you divide it by the mean. Okay, so that's why we have a CV here, coefficient of variation. Okay, so there's nothing new here. I don't think I need to talk a little bit more on this. Just a very briefly, calculation shows you can calculate this number as mean. This is the population variance. This is the sample variance. You take the square root, give you the SD. You divide them by the again by the mean, multiply by 100, and give you the CV. Okay, and that is what I want to say. Is there any question for this person? I think I'm done with this person. Okay, there's just to remind you, we have learned 5 different types of style. One is called range. Okay, biggest minus smallest. The disadvantage is subject to outlier. Okay, and I told you that you can use the same trick for the mean, use the Winsorized or truncated Winsorized or trim the data to solve the problem. Okay, the second one is interquartile range. Okay, and we learned 3 methods, but actually we just use the last one, method 3, to do the calculation. Okay, and this is consistent with the Excel or R, so that is why we use. And then we learn very popular method, variance, and his close friend standard deviation, and also his friend CV. Okay, and just a special reminder that there's 2 different versions. One's population, one is sample. They're the same, but that's actually one guy, right? Population one is the definition. The sample one is the one that we use when we do the calculation, but the goal is to guess what's going on in the population. Okay, so the sample one is just the method to do the estimation. Okay, that's a nice property. And just to remind you that when n is very big, population and sample that make no difference. Okay, I hope that's okay. Is there any question? So for the remaining 20 minutes, I hope I can finish shape. Okay. If I have time, I'll talk about correlation coefficient, but I don't have time. So I hope there's any question before we proceed. Is there any question? Let me check. There's a question in Zoom. No. Any question? If not, then talk about shape. Okay, and kurtosis. Okay. Now for these 2, I would say the formula is the actual formula to calculate is very crazy. Okay, I have to remind you that, but the original formula is very simple. Okay, the population formula is very simple, but the one we actually use in calculation, the Excel spreadsheet they use, is rather clumsy. Okay, and we don't need to remember anything, but we need to tell you what actually we want to measure and what actually used in practice is different. Okay, so the first thing is the first one. This one's called skewness. Okay, the skewness one actually is not super crazy. Okay, although look at this is okay. Oh, it's humongous object. Okay, but look at this guy first. Okay, this guy. Look at the numerator. Okay, look at the numerator. Okay, and you can easily notice that this guy looks like our old friend variance. Okay, variance is average square distance from the mean. Okay, this is average cubic distance from the mean. 3 times 3. Okay, raised to the power 3. So this guy you can easily see that this guy, when it's square, it's always positive, right? When it's raised to the power 3, negative remain negative, positive remain positive, right? So that means that if there's a number that's way bigger than the mean, okay, you raise to the power 3, this skew will be very positive, right? If other way, if the data is way below the mean, that some of them are mean, then this actually you calculate the skew will be very negative, right? And look at the denominator again, okay? This denominator is just the SD raised to the power 3, right? And you may ask why we're going to do it, because you only want to measure its skewness, don't want to be affected by its variance or SD. So you just raise to the power 3. Why raise to the power 3? Because you make this skew has no unit, like CV, right? CV has no unit because you divide by the mean. And we want it to be not be affected by its unit, right? So raise by 3. And not to be affected by its dispersion, so you divide it by its standard deviation instead of by the mean, right? So that's the reason why this formula. And you can easily see that if the shape is symmetric, okay, it will be 0. If it's right skew is not like this. Look at the graph here. This is a nice graph to be look here. If symmetric, this skew is 0. Okay. If like this, right? A lot of the positive here, that will be skew because mean is here, okay? And this number of data raised to the power 3 will make it very large compared to this number, which the power 3 will not be enough to compensate it. That will be positive, okay? And if you look at the other one, right? Look at this number will be way small compared to this guy because raised to the power 3. So that's why they will be negative, okay? So that is the what we have here is what we call the right skew, left skew. Okay, that's how we define based on the skew. Okay, and this is the skew formula when you write down what is the sigma. Okay, so this is how you do the calculation. Okay, and is that okay for this slide? Okay. And now here comes the difficult part. Okay. And we are going to do is you adjust. If you want to do actual calculation, you have to multiply by this funny part. Okay. It's a fraction square root of n times n minus 1 over n minus 2. Okay. And if you do this, that means that when you do actual calculation, this is the formula. I'm not going to detail, but this is the formula here, okay? And you probably don't need to worry about this formula, okay? I'm not going to do the detail, but you may ask why I talk about this. Is because Excel give you this, okay? When you call Excel, when you call the skew, this is what they give you, okay? And you may ask why we have this formula. Again, the same idea of sample variance or sample SD is when you do this calculation, this gives you the right skew. When you n is small, okay? You can see when n is big, okay? When n is big, this adjustment will be 1. Okay, there's no difference from 1. Okay, but when n is small, this will be different from 1. Okay, when n gets bigger and bigger, this will converge to 1. If you do calculus, calculate limit, and go to infinity, go to 1. Okay, that's not easy. But that is the idea behind. And when you calculate, it's very simple, right? Have n, M-1 or M-2. This is the sample standard deviation raised to power 3, and this is the formula here. Okay, and there's nothing but plotting in the formula. Okay, so that's why it's good to look at the example to show you how to apply it. Okay, sorry for the typo again. This is population. Okay, and with the data 1, 2, 3, 4, 5. Okay, I'm going to show you how you do the calculation by yourself. Okay, Excel. Of course, Excel spreadsheet will give you the same answer directly. Okay, you have data 1, 2, 3, 4, 5. Okay, you calculate the mean for each column. Okay, and you minus each observation from the mean. You get -2. 2 minus 3 gives you -1. 3 minus 3 0, so on and so forth. And you take square, gives you the other column here. If you take raised to power 3, you get this guy. Okay, and add them all up. This is 0. Okay, and even without any calculation, you know the skew is 0. Okay, and look at the data. You can see 1, 2, 3, 4, 5 is purely symmetric. So as expected, skew is 0, right? But you can also calculate the sample variance and sample SD, right? And you can plug in this guy over 5, right? And then do the same thing. This is the this guy here, and so on and so forth. Okay, I'm not going to go to detail, but this will be the we calculate. Okay, so you can, if you don't believe, you can go home and check. Okay, that's very simple. I'm not going to go to detail because of the time constraint. And look at the same. If you look at this data, 1, 2, 3, 4, 10, you can immediately see this is a right skew, right? Because the middle or the median is 3, right? And 1, 2, 3, 4 is 1, 2, 3 is a little bit close to the mean, but 10 is very far away, right? You should expect the skew is positive, right? So I'm not going to go over every single step here, but you can easily see the skew is 1.38, and the sample skewness is 1.6. So the sample one is bigger than the non-sample one. Okay. So that would be the calculation, and later we will, when we do Excel, we will show you why you get these two numbers. Okay, so you don't need to worry about the calculation when you do programming. It's there. Okay, it's already, you can calculate, but you may worry. I will ask you. Actually, I will ask you in your assignment. You will do the calculation. Okay, I'll give you some data. Calculate the skewness for me. Okay, so you will do it again. So don't worry. I think you get enough practice for this one. But I think the formula is very clear. Is there a question about the formula? I mean, there's nothing but the skewness. And probably you will ask why we care about skewness, right? Because of the fact that in general, okay, not always true, but in general, when we are skewed, right, the positive one, the median will be smaller than the mean, right? So that's why when we care about the average income in the population, we want to look at the median instead of the mean, right? We look at the middle guy is more important than the distance in the middle, right? Because we don't care about in total average income, we are not worried about underestimation, right? We worry about overestimation, right? Overestimation income, we make a big mistake. Underestimation is not a big deal, okay? And when the negative skew, we're other way around, okay? So that gives you an idea why we care about skewness, right? And there's several reasons why I want to care about the skewness, okay? And as I said, in the financial crisis in 2007, people said people don't take into account extreme event, okay? An extreme event that skewness can tell you that it's important. Okay, and later actually that related to kurtosis we talk about very soon. Okay, and the skew is important. The skew that is a very important measure. And second one is related to human decision. Okay, people in general would tend to exaggerate small probability event. Okay, what I mean is when look at the tail, you would think it is higher than it should be. Okay, look at lottery. Although it's very unlikely that we win lottery, right? But we will still buy it because we think it's more likely than it should be. So when it's skewed, then you have to be very careful. And the last one I think is very relevant these days is for actually have been shown in the literature, empirical fact is for the stock that has been shown have a skewed return, pop skew return, then actually carry premium. What it means is if the stock is a crazy stock that is go up exponentially, have a lot of growth potential, then you will carry a premium. That's why you can see tech stock or stock with startup or unicorn stock, they get a lot of premium. Okay, why? Because there's a lot of growth potential. It's very unlikely, but it's likely that they will go a lot. Okay, so that's why I think just recent or few years financial literature have shown this. So in the old days, we look at financial literature, they look at the mean or the variance, but now have proven that the skewness is also important. Okay, I don't think it's recent finance theory taken into that, but research has been shown that, but yeah, not been taken into practice. But people in actually investing know skewness is important, right? They look at the Tesla, right? They look at all the recent a lot of crazy stock bubbles, then they would have. If you notice, you will see them. Okay. So I think I still have 5 minutes. I think I can talk about the last one. If I don't finish, it's okay. But this one, if you look at this formula, we call kurtosis. Okay. Look crazy, but if you compare to skewness, it's nothing but instead of 3, you have 4. Okay, so there's nothing new here. If you happy with kurtosis, skewness is just raise the power 4. Okay, and you may ask what it is, right? Again, why we care about this guy? Okay, and as I mentioned, this kurtosis is thickness of the tail. Okay, is whether the tail is fat or thin. Okay, and fat or thin is compared to normal. Okay, and later we will see what normal is. Remember the bell-shaped curve? Probably you know it from your high school. And look at the normal bell-shaped curve. This kurtosis for the normal is always 3, regardless of the mean and variance. Kurtosis is 3 for normal. Okay, and that means that we would define what we call excess kurtosis. Okay, that is calculate kurtosis minus 3. Okay, and if you have more than 3 or excess kurtosis more than 0, we call fat tail. Okay, and if less than 0, we call thin tail. Okay, and there the Greek terminology refer to this is called mesokurtic, leptokurtic, plakurtic. I'm not sure you need to know this, but usually we'll call excess kurtosis is 0, more than 0, or less than 0, or people call fat tail or thin tail. Okay, and why we care about this is because we learn the normal bell-shape often used, right? If your data have a very big excess kurtosis, okay, the traditional idea that adding 2SD, adding 3SD things will be problematic. Okay, and if your data actually or the stock you invest has a big fat tail, okay, actually you are having a stock have a high risk, right? If your stock has a very thin tail, then actually it's less risky than the variance suggests, right? So that is a very important measure, okay? And look at normal, look like this. The blue one is a normal one, okay? When you have a fat tail, okay, is the red one. When the thin tail is the brown one, okay? And although we don't emphasize later in this course, we will also work on the normal regime where assume normal will apply, okay? But in the practice or later in other classes, advanced classes, you will learn is when this doesn't apply, things getting some issue there, okay? You have to be much more careful, okay? And I'm sorry for the crazy notation here, okay? When you have kurtosis, okay, when to estimate, you have to calculate this guy, okay? And of course, if you Excel spreadsheet with you, have no problem because Excel spreadsheet give you this exactly, okay? And why I want to give you this is this formula doesn't look familiar, right? But remember, this is just measuring the excess kurtosis, okay? So this is the sample excess kurtosis, okay? And this will be the calculation. I just very briefly go over with you, right? Again, this is data, right? This is the mean. This column, you calculate each observation minus the mean. And you take square to the last column. And you take square again from the last column, right? And this will give you this guy, right? You take square again, or you click 4 times to get this guy, okay? And you can calculate the sample variance, okay? And you calculate this guy, okay? And kurtosis will be just this number, okay? Over N5. And this number 10 come from here, okay? And over N, and take the square, okay? And it give you 1.7, okay? And you minus 3 here is negative 1.3, okay? So that means that this number is actually a thin tail, okay? Actually, you can see it because the mean is 3, okay? And the SD is like 1 point something, okay? Okay? And you can see every observation is within 2 SD, okay? Nothing beyond 3 SD, right? So normal would tell you more than 3 SD, you still have something, right? So that means that this is less than, this is much thinner than, the tail much thinner than normal. So excess kurtosis is less than 0, okay? And then you can apply the same formula, which I agree is like crazy, okay? But there's nothing but put the number there, okay? And I told you this Excel will apply, right? Except for your assignment or your test, we may ask to calculate this. Otherwise, when you apply in the practice, you just use a formula. So you don't need to worry about this, but at the end, you calculate this is negative, which is not surprising because the unadjusted one is this one. So it's negative. So this is what we have. Okay. So I think I should end here. You can see if I have this number, I'm not going to repeat, but kurtosis will be positive. Okay. I guess I should end here. I will maybe just give me 30 seconds. Okay. And why we care about this is, as I said, for insurance, you care about extraordinary risk, okay, or rare event. So that's why you care about kurtosis, okay. And for insurance, you care about earthquake, flooding, or pandemic. If you don't take those into account, then your company lost money. Okay. And again, for income distribution, we care about Gini coefficient, and kurtosis is also an important way to use and the modeling setup. Okay, but I don't want to take up more your time, so I will see you next week. Happy Mid-Autumn Festival. I stay around to answer any question you might have.
That is, how about the group media? I know there's maybe King's method, Pearson's method, and Simpson rules.
So the median?
Yeah,
Oh, we just use this one.
this is this one.
Yeah, just this one.
How about the group data?
We just group data just count it at the same number. We just say suppose you have group data is like you have 1, 1, 2, 2, 3, 3. Please then count them the same. Yeah, but say this is I have 1, 2.
I'm sorry to interrupt. Are you the lecturer here?
Yeah.
Yeah, I am the next one, and this is the first time I'm using
Yeah.
this. So if you don't mind, I'd like to.
Yeah.
Right.
Yeah, sure.
Sorry for the interruption.
And the Zoom.